So first thing is that, like it happens with me all the time, I was incredibly ambitious when I sent the title and the abstract. I wanted to tell you everything, but that's not going to happen. I prepared the talk and it's 182 slides. And even that doesn't cover all the things we have done here. I have not been giving talks at all for the last 3 years for purely personal reasons. So I got a bit carried away, but I would talk about things in some completeness. And then I'll talk about things we are doing now. 2 of my students who are doing some of the work are in the audience. So if I cannot answer questions, they will. So I changed the word correlation to interaction. You'll see why. So I'll talk about twisted bilayer graphene, both bilayer and double bilayer. I'll not talk about double bilayer. The physics is very similar. I'll talk about twisted transition metal dichalcogenides, which have some similarity and some difference with bilayer. And Haining Pan, who's in the audience, the graduate student, did some of the work. Fengcheng Wu, who was a very good postdoc here, came from Alan McDonald's group, just left 6 months ago. I'll talk about some of his work. In-Wei Wu, another very good student at Maryland, also in the audience. I'm going to talk about some of his work. And I have one slide showing Jed Pixley and Justin Wilson's work, because that work, I think they can represent. And then there is a whole bunch of renormalization grouped another type of work which I have done in this system with a lot of people that I will not talk about at all, because there is just no way to fit them in the scheme of what I have. In case so I will not talk much about topology. And the reason being, the word topology now is needed to publish anything in glossy magazines. But in the context of what we are talking about, topology is not anything profound or deep. It's certain integrals of band structure having non-zero values. It's really that. And then you call that a Chern number and so all kinds of things. And some of the things I'll talk about have a Chern number, some don't. And I'll mention that, but I'll not talk much about topology. I'll really talk about physics of interaction and incommensuration. So I just wanted to quickly tell you that in preparing this talk, I was a bit taken aback by our productivity on this. I didn't realize that we actually have, I'm not going to go through all these papers. We actually have 16 papers in last year and a half in this subject. Now you may say, how can one person have 16 papers? Obviously one person did not have 16 papers. I counted, there are exactly 16 people involved. I have 15 collaborators. I collaborate with a lot of people. We have a large group here, nowhere near as large as in Flatiron, but we have 30 people here in our center. And then I have had so many incredibly generous and incredibly good ex-collaborators like Jed Pixley, Justin Wilson, Yuhian Wang. I collaborate with them. So that's, so it's not as bad as it sounds. It's one paper per person for 1.5 years, okay? So we will have one very soon on interaction range dependence. And I really would like, if this group at Flatiron gets involved in this thing, we do not have the know-how and the computers to work on this in a big way. And I'll try to emphasize things where it'd be very good if this computational center of Flatiron, where of course there are top theoretical physicists, get involved. So I'm going to start by showing you some slides that all of you have seen many times. So I'm not going to spend too much time, because if you do not know these things, you probably would not get a lot out of this talk, but I'll still explain. So this is a figure taken from, actually, this is a photo of the Spanish group, because it's rather appealing. It's like the 3rd or 4th group that started working on it. So what I'm showing you here is the resistivity, simple transport, very low temperature, 20 millikelvin resistivity of a sample. It happens to be twisted bilayer graphene, but for our purpose, that's not very important. What is important is to notice all they are doing is changing density, which you do in a semiconductor just by changing a gate voltage. And what is going on, how rich the physics is. So there is some place where you see, not much is going on, a little bit of insulating behavior, a little bit of insulating behavior. But then there are some places where the system is going superconducting. See, resistivity falls to 0. So there are these peaks in resistivity are like insulators. There's a minimum in resistivity of superconductor, but these have been verified with better experimentation looking at Fraunhofer pattern and how the resistivity depends on temperature. So in one sample, this is the phase diagram, take it with a grain of salt, you are seeing superconductor and insulator both, but mostly superconductors here at various doping. Now, what do these dopings correspond to? It turns out these insulating phase and superconducting phases correlate with how many electrons per unit cell you have. 1 electron, you see something, 2 electrons, you see something, 3 electrons, you see something, 4 electrons, you see something, and 4 electrons, you have filled the unit cell. And here is data from the original experiment, the seminal experiment of Pablo Herrero's group at MIT, who first pointed out that you see superconductors and insulators both, just as you change the number of electrons per unit cell. So this is like a dream correlated simulator. I would say I have worked on these cold atom simulators. I know Atwan has worked on it also in the past, beautiful systems made by people like Emanuel Bloch, Marcus Greiner. But this system to me seems to be quote unquote much better. Maybe I'm biased, I'm a solid state physicist, but what is better here, I'm not being facetious, is that you have many more knobs. You can change angle, I'll explain what that is. You can change temperature, you can change density, you can apply magnetic field. So in your Hamiltonian, you are changing many more things. So it's more rich. And to me, the most important thing here is, unlike in cold atom system, the Hamiltonian here is not precisely known. Okay. In cold atom systems, you create your Hamiltonians, you know it precisely. So you're never going to get new physics. You're only going to get physics you put in from day one, which is good, of course, because you'd like to know, how some specific models behave. But I would like to know much more, since I cannot compete with Flatiron Institute. If the model is well defined, Flatiron will do the work long before me and much better than me. I would like to know what happens. So the model is kind of like a Hubbard model, but not quite. And that's where these systems are amazing. So what is this system? System is very simple. You take 2 graphene layers and you just twist them with respect to each other. And in doing that, you flatten the band. Okay, that's what is going on. You flatten the band, and you flatten the band, you are reducing your interaction energy, correlation energy very little, but you are reducing your kinetic energy exponentially. So the ratio T over U goes down enormously, or U over T goes up. So this was actually already pointed out a long time ago. This is one paper that's very well known, but even before this, the papers by Pacogini and others who pointed out that if you take 2 graphene layers and you can twist them, then you basically create a Moire system. And all you do is that you create a new system whose unit cell is 50 or 100 times the original unit cell. What was pointed out in this paper, that in some situation, you can really bring the velocity down all the way to 0 for some angle between the two. Well, I mean, velocity may not go to 0, but it goes down enormously. And if it goes down enormously, you have increased the interaction effect enormously. I should have actually predicted all these things, but I'm not smart enough. I wrote a rather well-known paper in 2007, on Jung-Woo's work, which I spent 6 months in Santa Barbara. And we realized that if you can create flat bands in honeycomb system, you will have very strong interaction. We actually did some exact analytical calculation. I mean, Conjung did it. And like most theorists, I mean, I'm not as careful as Andy Millis, but I'm somewhat careful. So we kind of wimped out. We said, this is a very good system to see Wigner crystallization. We are not imaginative enough. And you may think that, well, Leon Balance is very careful, so he did not want to go, hawk crazy. Here is Alan MacDonald. This paper, which is very, very well known, cited more than 1,000 times. After doing this band structure calculation, showing the velocity may go to 0, well, the hopping amplitude may go to 0. So there'll be very strong interaction. What does he say in the last sentence of the paper? Well, maybe this would give counterflow superfluidity or flat band magnetism. Even he was not brave enough to talk about superconductivity, Metal-insulator, all those things, okay? So theories came close, but you're not brave enough, so this is very good. This is unlike all of topological physics over the last 20 years. All of topological physics over the last 20 years is free fermion theory, and then experimentalists claim to see it often with considerable confirmation bias. Here, theories came close, but did not predict the right thing. Experimentalists led, which is the classic condensed matter phenomena we like, right? So here are some data. This is from original experiment of Pablo Harrero. Resistivity measured as a function of temperature, sample MF4, some fixed angle. I think the angle here is 1.16 degree, very close to the so-called magic angle, which is 1.08 degree. And what you find, look at this absolutely straight resistivity going up. These are all somewhat different density. As you see, density is changing from 1.2 to 1.89. They're absolutely parallel. So d rho dt doesn't depend on density, but the resistivity does. And superconductivity happening at low temperature, okay? So above superconducting transition temperature, you have this absolute linear resistivity. This is the first problem I'll talk about. And then in some situation, just slightly away in density is going insulating. If you focus in this region, what you see, superconductor at some density, insulator at some other density. It's like incredible, right? This is what happens in high TC, but here it's happening in one sample. In high TC, you have to do in different samples. Change the doping, chemistry is changing. Here, all is changing is just a knob. This is was the theory's dream. And so here is superconductor, here is insulator, and here is a strange metal. This is a strange metal because resistivity is linear in temperature, density independent d rho dt, a bit similar to what happens in cuprates and some other materials, but much, much more spectacular. Now, when you look at these resistivities are huge compared with graphene, okay, huge, kilo ohm. So this was the first thing I'm talking about, strange, okay? I'm going to talk about strange first. Well, not necessarily strange beauty, but at least strange metal. What is going on here? Obviously, there is some physics here. Resistivity is absolutely straight, linear, parallel, no density dependence, and resistivity is very high. So let's try to understand this first. And I'm going to explain what is Planckian dissipation. Before trying to understand metal, superconductor, and insulator, which obviously is strong correlation physics, let's go to slightly higher temperature and ask what's happening in transport. And the way I got involved, by the time I was, as you all know, far too involved in Meorana, to often think about anything new things. And Andrea Young sent me some data. I may even have the data here. I think I do. Let me just see if I have the data. Yeah, send me these data and ask me if I understand why the resistivity is so high and so linear. And I did not notice this in the original experiment. And I told him right away, I know exactly what is going on. And it turned out that at least we still believe that's what is going on, although I do not think that Pablo agrees with me. So we'll see. So he's
excuse me, one second. One second. Was there a question?
Yes, there was a question by me.
Yes.
Hi. Yes, Sankar, just a question about the resistivity. So I think what's plotted is the sheet resistivity.
Yeah.
And I agree with you that it is quite high, but it's not as high as the quantum of resistance, right? So if I had to extract a mean free path from this and compare to the Moire-Feigl criterion, I would still be below, correct?
I'll talk about those things. Yeah, you'll still be below here. This is a very good, important point. So this is not a bad metal in Kifelson standards. Yes. And I actually use that a lot, okay?
Good.
That I should be allowed to do the kind of theory that Sarma does, okay? Which is very
help to keep a bad metal for metals that have a,
I will, because of Antoine, you obviously make a very good point. I will mostly talk about d rho dt because it's sheet resistance, not resistance per square and so on. Okay.
Exactly.
So is this a strange or bad metal? This is exactly the question you just asked, okay? So resistivity is linear in T down to some low temperature. And low is in inverted quote, low is in the eyes of beholder, okay? So I'm going to explain this. And the first point made by MIT, and I had to really struggle with them explaining this, is that they said, look, the Debye temperature is 500 Kelvin here for graphene. This is very, very low. Well, Debye temperature, the textbooks are wrong. Debye temperature has nothing to do with down to what temperature resistivity is linear in electron-phonon model, and I'll explain that to you, okay? So low it in inverted code. Linear in T behavior is over a large range of temperature. Very high resistivity, again within inverted code because of what Antoine commented, okay? Approaching metallic MIL limit, but staying below, okay? Transport scattering rate is KBT, and a very big deal is made by people on this. I don't know if you guys know, it upsets me enormously, because by this definition, and I have said this to people like Sean Hartnell and so on, every regular simple metal is Planckian, because every regular simple metal transport scattering rate is 2-3 times this, okay? And then I'm not going to talk about non-Fermi liquid and those things, because as Antoine just said, these are all below the MIL limit. So, all these things, because people who are working on it are very smart, they usually ignore phonons, but I'm not going to ignore phonons, because 99% of metallic transport, maybe 99.9% of metallic transport can be understood using phonons and impurities, but in a very different context. So that's what I'm going to talk about. So what do we know? We know resistivity is linear in T, and we know at some low temperatures goes superconducting, but resistivity sometimes stays linear down to 4 Kelvin. Can we understand it using electron-phonon interaction? And I will argue that yes, we can. So here is sheet resistance, and here is d rho dt. And d rho dt sometimes could be very high, typically of the order of 100 or 200 ohm per Kelvin. This is data from, in fact, Columbia Corey Dean and Andrea Young's collaboration. And since I know both of them from their first year in graduate school, I had access to the data long before they published it. We had a lot of conversations. And in fact, this figure here is the figure Andrea sent me to ask me, can I understand? This is the very first data in this subject I paid any attention to. And I immediately said, I completely understand it. Why do I completely understand it? Because I wrote a paper with Yuhyun Wang in 2008, where we calculated the resistivity of graphene, regular graphene, taking into account electron-phonon interaction. To my amazement, this paper has become one of my most cited papers ever. It's approaching my most cited Phys B paper. But this was a serious calculation, completely solving Boltzmann equation, putting all the numbers in. And do you see the resistivity here? 1 ohm. And do you see the resistivity here? They're more or less similar size, 1000 ohm. Resistivity is 1000 times higher. This is the first thing I noticed. Resistivity 1000 times higher, and d rho dt is also 1000 times higher. So in regular graphene, this is measurement by Philip Kim when he was at Columbia, and the same Efetov, who was a Columbia graduate student who is now doing these experiments in, this subject, you go back to the same people. Efetov did this experiment in Columbia. I'm sure Andy knows him. And now he's doing these experiments. And this is a very beautiful experiment. Actually, Philip Kim, there's a very interesting anecdote behind it. Philip Kim was actually trying to get superconductivity by going to the actual Brillouin zone boundary of real graphene. You have to go to 5 times 10^14 per square centimeter density to go there. And he could not quite achieve that. So he did a transport measurement and showed that his data agree quantitatively with our theoretical prediction. And one could see Bloch-Grüneisen behavior, this linear in T behavior. I'm going to come to that. So d rho dt in regular graphene is 0.1 ohm per Kelvin. Here, d rho dt is 100 to 500, okay? 10,000, all you have done, it's graphene still. All you have done is twist it slightly. I mean, it's pretty amazing if you think about it. I got goosebumps when I realized that I may have a simple understanding. And also linear behavior goes to 10 to 20 Kelvin. So metallicity, if you want to call linear behavior metallicity instead of strangeness, I call it metallicity. This is my definition of a metal, because all metals behave this way. Resistivity is linear in room temperature. So it's extreme strangeness. Okay, so let's try to understand this. So to understand this, I went back and took help from Yuhyun Wang, who is now a very senior professor in the Samsung University in SKKU in Korea, where they do a lot of work on graphene. So I went back to our paper, and it turns out that we could write down an analytic form for how resistivity behaves at high temperature. It's almost like a textbook calculation, but actually done. It's linear in resistivity, proportional resistivity. It's proportional to the electron-phonon coupling constant squared. This D is proportional to what is called lambda. In semiconductor, it's deformation potential coupling. And then a whole bunch of other constants coming. So these are the spin degeneracy 2, valley degeneracy 2 in graphene. Rho m is atomic mass, same in Moire. All of these quantities presumably are same in the Moire material, twisted graphene as regular graphene. Phonon velocity may change slightly, but there is one quantity, Vf squared. This is a formula I knew by heart because I derived it, 1 over Vf squared. So when Andrea sent me the email, I immediately asked him, is your velocity about like factor of 50 lower than regular velocity? He said, yes. I said, well, then I predict you're going to see a factor of 2,500 increase in d rho dt. And he said, that's exactly what I'm seeing. And textbooks say that resistivity is linear for temperature above Debye temperature. That's completely incorrect, by the way. It's not Debye temperature. First, it's not Debye temperature. It's Debye temperature over 5. When you do the actual asymptotic expansion correctly, you have a factor coming from the special functions. So it's of the order of Debye temperature is factor 5. But really what it is 2kF scattering, because 2kF scattering controls resistivity. So it's the 2kF phonon. 2kF phonon is this quantity, 2 h bar VFK, whatever its energy is. Now you say, why do textbooks say Debye temperature? Because this quantity regular metal is much higher than Debye temperature, much above the cutoff. So in metals, it's indeed Debye temperature because Debye temperature is lower than that. But over here, density is very low. In a metal density 10 to the power 23, here the bulk density is more like 10 to the power 17. So this number is actually much, much lower than Debye temperature. So you can go to very low temperature. In fact, at low density in gallium arsenide, this could go down to 100 millikelvin. I have papers going back to 1990 showing that you can have linearity down to 100 millikelvin. So we just took our old theory. This is our old theory, and did a full calculation, and old theory, Efetov and Kim verified it explicitly quantitatively. And we did this putting in the new band structure of twisted bilayer graphene. We said, let's just do this. We are not going to publish a paper saying, oh, velocity goes down by a factor of 50. So this is our band structure calculation of velocity. So this is the magic angle where the velocity is 0. When the Fermi velocity is lower than phonon velocity, our theory really doesn't apply. So let's leave this part out. But when it's above, it applies. And we can now calculate, and velocity depends on the twist. So we can predict the twist dependence, we can predict the density dependence, and we can predict the temperature dependence. So this is the theory. We should read the paper. This is something I know what I'm doing. All the people who used to do electron-phonon resistivity calculation, like my good friend Phil Allen, great scientist at Stony Brook, I communicated with them. They did not see anything wrong in what I'm doing. And they are all retired, and some of them are dead, unfortunately. So I'm the only one still doing this sort of kind of calculation. And let me just cut a long story short. This agrees well with experiment. That is not proof that what we are saying is correct. Okay, that's just a necessary condition. It may be something else. I cannot rule that out. Okay, so this is our calculated resistivity.
Yeah.
And you can see that resistivity has very strong angle dependence. This very strong angle dependence is coming entirely from the band structure changing, or if you want to do a very crude back of the envelope calculation, from the velocity changing, graphene velocity changing. And d rho dt show this remarkable behavior. And this is the regime of ordinary graphene, somewhere 2 degrees. And this is entirely arising from band structure. So it's not just more angle enhances correlation effects, U over T. It actually enhances electron-phonon interaction even more, because electron-phonon interaction goes as square of the interaction, not just linear, So, but of course, T goes down exponentially. I'm going to come to that. And here is the density dependence. It does not depend on density at all at high temperature, because as you see, this formula that I showed you, the analytic formula, there is no density here at high temperature, okay? Just velocity. At low temperature, of course, there is a density dependence because Fermi momentum comes in, coming through here, this function through Kf. And sure enough, at low density, this bending, where that happens, depends on density. Higher the density, this bending, which is called Bloch-Gunaison behavior, where it's not linear anymore, that happens at various places. And we actually have a prediction that it should really be 10 to the power 4. And that kind of applies, but they do not have enough dynamic range to predict, okay? And there is a big argument going on between me and MIT people that what does this bending happen? Does this agree with Bloch-Gunaison, this simple formula depending on Kf, or is there some other physics there? And this I don't want to get into because there is not enough data to really pin it down. So
may I stop you at this point and ask two questions?
Please.
So the phonons that you're considering here are essentially the acoustic phonons of graphene, if I understand.
They are acoustic phonon of graphene, not essentially. Our calculation is acoustic phonon of graphene. Okay, but
now there's been a lot of discussion in the literature about the phonons associated with shifting the bilayers.
Correct. So I'm coming to that. So it's phonon of graphene, but for the two layers, you have to take into account there are two layers. And now that there are two layers, you'll have symmetric and antisymmetric modes of graphene, and you take those things into account, and the whole thing now boils down to if small gaps in the phonon spectrum are opening up because of this, because of tunneling and so on, some of those effects are not included in our paper because people who have done this calculation, this I forget his name, late Shucheng Zhang student at Princeton. He's now an assistant professor there. We talked to him extensively. Those effects are small. But Andy, as usual, went to the heart of the matter. Some of those questions are still open, and they require serious computation. Okay? They require very serious
Yeah, I'm sorry, but may I ask that in addition to that, there has been a lot of discussion that I don't have my mind around about sliding modes that have to do with sliding and twisting of the layers with respect to each other, which may also affect the electronic structure and therefore scatter in funny ways.
That's absolutely
correct. Is there a clear picture of that these days, or?
No, we take the standard Bisch's or McDonald band structure. So we are not taking into account any relaxation. Yeah, we are not taking into account any relaxation. And all those things should be done. Okay, we don't have the ability to do those things. They should definitely be done. Okay, and these are the questions referees asked. That's, I think, part of the reason paper didn't come out in Resistivity. These are all genuine questions. And my gut feeling, based on my intuition of doing these things for 30 years, is that those things will surely change the numbers, change where this is shifting, maybe change the slope a little bit. But I simply don't see how that's going to change the whole physics, that this physics will go away, unless there is something very big I'm missing. Okay, so and you should think of this as really the zeroth order theory. Okay. So this is the first paper in the subject. So, but these are all good questions. Okay. There is a sociological reason I did not do those things also. What's the point? People who want something exotic, something magical, even if I do those things, they're not going to accept its phonons. They will say it's strange, no matter what. I have experienced that many, many times, okay? With, for example, Kravchenko's two-dimensional Metal-insulator. Doesn't matter what I do, what agreement I show. Those who want exotic, nothing will satisfy them. So that's another reason I did not want to punish my students and post it. But we really don't have the computational part to do these things. It should be done. Jet Pixley should do it in collaboration with your center. So this is, Andrea Young and Corey Dean's data. Beautiful. Now you may say, what's going on here? Why is at high temperature it goes down? This caused a lot of problem in the beginning, and then you understood what's going on. It's actually something very simple. There are other bands in twisted bilayer graphene, which are not taken into account here. The higher bands, all the electrons just move to those other bands, and it looks like resistivity is going down. So it's an artifact. Okay, so this is completely understood. All right. So let me just summarize, okay, for you. So this is the high temperature result. Agrees well, but I will now be honest because Andy and Atuan have asked me questions. So I don't want to lie to you. I want to only claim good qualitative agreement. Quantitative agreement is only if I take this factor from graphene D, the same factor we needed to get agreement between original Huang-Sarma 2008 theory and Efetov and Kim experiment in ordinary graphene, and multiply that by a factor of 2. So the coupling, we still need a factor of 2, meaning our knife theory, Andy, gives resistivity factor of 4 off. And all of those things may be coming from your questions you are asking. It's not very well known, and this is what Andy just asked me. Moire may affect phonon. It may affect the band structure much more. And estimate of people who do these things, so that Moire may affect phonon parameters by 30%. This is what I have been told, but this is not my work, okay? The other thing that's not very well known, among theoretical physicists, is that deformation potential coupling is a very, very difficult thing to measure experimentally. They measure it from optical experiments. And when I was doing gallium arsenide, you think in gallium arsenide, these things are completely known. No, in gallium arsenide, throughout the 80s, there was big fight between optical people like Cardona and people who do transport. The numbers were quite different. Numbers were factor of 1.5 different, which in resistivity is factor of 2.5 because it's square. And my student at SOCOM would actually fix it by doing very careful transport and comparing it with Bell Labs data or Stormer's data. And we found that the actual value of resistivity is actually in between. D is in between. So what I'm trying to say is something very simple. Deformation potential coupling is not so easy to measure. So when you say factor of 2 off, it sounds awful, but it may not be so awful. Here is comparison. These dots are data points taken from experiment. And remember, our theory doesn't apply below some point here. And solid line is taking naive graphene parameters for phonon, as Andy just asked me, and shifting it by 2, we get slightly better measurement, but our theory fails once the velocity is higher than once the graphene velocity is lower than the phonon velocity. Was there a question? No, okay. So this is where we are. And so there are still some questions, no question about it, but I think we have a crude picture. And I would love to see somebody improve this. So this is a better thing for the same thing. Here is our result. This is the key result. It includes Bistritzer, McDonald level band structure calculation. And this is, a better way of showing the data. I think finally in PhysRev, we put it this way. And this is the key message, that resistivity is proportional to temperature. For temperature above TBG, this TBG is the same TBG as in graphene because it just depends on KF. And the theory is valid only when our Fermi velocity is higher than phonon velocity. This is sound velocity. Now, one question immediately comes up. If we take this definition of D and convert this thing to an effective lambda, dimensionless coupling constant introduced by great Macmillan, long time ago in mid-60s, to talk about superconductivity, then it's known this lambda transport is very close to lambda BCS. So suppose we say that if it's phonon mediate mechanism, suppose we say superconductivity in this system is coming entirely from this, let's call this Huang-Sarma mechanism, phonon and low Fermi velocity. Suppose we insist that. Well, then you have a prediction, because lambda, we can take lambda from here without doing any theory at all. And we can just apply BCS theory and get the superconducting transition temperature. We get a number like 1 Kelvin, okay? So, and this is already in our paper, and I'm going to come to superconductivity next, okay? So what we have explained, conclusion within inverted code, because all the caveats that Antoine and Andy brought up apply. Strange metallicity, again within quote, linear interresistivity down to 5 to 30 Kelvin. So one argument between MIT, UCSB Santa Barbara, UCSB Columbia, and me is sometimes in some of the samples, and this is an important point, open question, sometimes that linearity in some of the samples go down to 300-400 millikelvin. factor of 10 or maybe even factor of 20 lower than what our theory predicts. Okay, we do not have an explanation for this. Factor of 2 or 3 I can explain, but I openly admit that if your linearity down to 50 millikelvin or 100 millikelvin, I do not know where it's coming from. I have a guess, and I can tell you my guess. I'm working on it in the context of transition metal disulfogenides, Pasupathy and Corey Dean's work. Magnons may be playing a role also. Magnons also scatter. Magnons also give resistivity. And if low temperature, once the phonons have gone down, if magnons are contributing, you may see nonlinearity a bit down. But whether that's going on or not, I do not know. It's an open question.
So, Sankar,
why magnons? Because there is anomalous ferromagnetism here. Very large linear resistivity, d-rho-dt very high, 100 compared with 0.1 in regular graphene, rapid increase of d-rho-dt with twist approaching magic angle. All these features are explained by electron-phonon scattering, but I have given you the caveats that quantitatively there are still some questions.
So may I ask a question related to this? One feature of the linear resistivity is if I have a linear regime, I may then extrapolate to t equals 0 and ask what would be the extrapolated value.
Yep,
and this of course depends on extrinsic things like impurities. But
I'll show you
for phonons, there's an intrinsic one value. Is there information in that in the available data?
There is some, and Vivian Wang and I did a calculation, and we have results. But experimentalists are very interested in this particular question because they want to see all the correlated phases and so on. So I have not been able to, other than one person. So this is an open question. Okay, but I'm going to show you our calculation doing exactly that. Okay, the extrapolated value, what should the extrapolated value be? Because we have pretty good idea the level of dirt in graphene because of all the work. So it's a very good question, okay? And I'm going to show you something on that. So d-rho-dt is 1 over Vf squared. Planckian bound can be violated by low density and large electron-phonon coupling. Dimensionless coupling is, you may say, why do you have saying gigantic? In monolayer graphene is 0.01, and here it's 1. And BCS critical temperature is consistent, meaning of the order of a Kelvin. So let's go to superconductivity. Let's go to superconductivity. Because the question that you're interested in,
before you get there, may I ask a question about these?
Please ask as many questions as you want. Yes, please.
Okay, so I have 2 questions actually. The first one is, great. I mean, this indeed emphasizes the key role of phonons in this story. But where do you view the role of correlations in the temperature dependence of resistivity? Do you think they are just not important, or what? That's my first question. And the second question is, I don't completely understand in what sense you are saying that the so-called Planckian bound is violated. I mean, there is a question. I mean, do you mean the prefactor can be large? That's what you mean? Because it's all T-linear, right?
Yeah, that's all I mean.
That's what you mean.
Right, that's all I mean. Yeah. If lambda is 1.
When it comes to this prefactor, there is kind of a hairy debate as to whether one should use the quasi-particle lifetime, hence use the effective mass in the analysis of conductivity, or the bare mass. I mean, what's your take?
Yeah, here those things really do not come in. So I would say that this is like regular metal. So yeah, so question you are asking is that, do we know how much graphene velocity changes from electron interaction effect and so on? So in our paper, we speculate on all those things in the appendix.
Well, not only that, I'm just talking about the electron-electron scattering, the electron-electron interaction contribution to the scattering rate.
Right.
Which should also show up.
So let me answer your question. I have thought a lot about it, and I have an analysis of physics paper speculating precisely on those things. I didn't want to go into those details. I have a very long analysis of physics paper with Feng Cheng talking about it. You should look at it, okay? But first, maybe give an honest answer. These questions are not answered at any level of satisfaction. These are very good questions, okay? So I speculate various possibilities. Now, answering a question rather directly, I would first answer that it's Planckian in the sense if lambda is 1, as in some of the regular metals, let's say lead, then Planckian bound, everybody would agree, is violated by 2 pi, okay, because it's 2 pi lambda, okay? So, and that doesn't go away, even if you take into account regular many-body renormalization effective mass and so on and so forth, okay? Because that's like 20%, okay? So smart people would say, yeah, but that's well understood. So that has nothing to do with Planckian behavior. We are talking about electron-electron interaction. So that applies here also. When I say Planckian bound, I'm just talking about this 2 pi lambda, okay? So that's what I mean by my statement here. Now let's come to a more now let me come to a more serious question. What is correlation doing? Okay. One thing you can argue, an ex-postdoc of mine argued, claiming I'm wrong, so I'm not talking to him anymore, because he did not do a calculation. You can say, what about screening? You can ask that question. There are all these electrons. You know, screening is a part of correlation. These are all different words different people use. You know what it is, right? If we solve the electron-electron problem, there is the screening, correlation, renormalization. It all comes at different places. It's like 10 blind men looking at the elephant, right? So since I have done a lot of work on electron-electron interaction in phonon, and screening is sometimes important, sometimes not. What is screening? And if you just use screening naively, you'd say, oh, this lambda should go down. You know, using my own theory, it's fine if you do that. But the problem is this, that naive static screening theory, Thomas Fermi screening theory, doesn't apply here at all. So even if you say there is screening, you have to do full Eliashberg theory, because it's very dynamical, because the energy scale of the electrons are comparable to the energy scale of phonon. So there is no Thomas Fermi screening. And as we know, on the textbook level, Thomas Fermi screening always overestimates screening. Dynamical screening sometimes gives you anti-screening. Interaction may even go up. And this is why I told Shafiq Adam that you cannot just take one of my old papers where Thomas Fermi screening is perfectly okay and say, look, Kawamura and Dashama showed in 1990 that electron interaction reduces this. You have to do the full calculation, and this is an open question, okay? So correlation effect should be included here, even leaving out, and I'm going to come to that, even leaving out direct effect of correlation on scattering, transport, just for the phonon part. We did not do that, okay? Now, answering your question, what about electron-electron scattering itself? Because after all, Brillouin size is very small. You expect a lot of club here, or maybe there is club here. Electron-electron should contribute. Yes, I have no comment on that, other than saying there is no sign of a T-square anywhere. No one has seen any T-square anywhere, at no density or anything, okay? That's all I can tell you, okay? So I did not look at it, okay? But this is a very good question, you know? You guys should think about it, because I worry that is it possible that all this effect is coming from very complicated electron-electron scattering effect. It's just coincidence that our numbers are nearby. Phonon effects are screened out completely. And what is happening is very heavy clap. And I know what calculation needs to be done, but that requires a serious computing. Okay, did I answer your question fairly honestly?
Yeah.
Okay, all right. So let me now go to superconductor.
Sorry, before you go on,
yeah.
Can I ask a quick question? Just actually in terms of the experiment and the phonon renormalization due to twisting, is there any estimate just from AB stack twisted, or not even twisted bilayer graphene, just bilayer graphene? Is there any estimate of like interlayer tunneling and on the phonon scale? I mean,
my understanding, I'm not an expert on it. There are not too many phonon experiments in graphene, unfortunately. The effects are that 30% level, I said. So
they don't know.
Yeah, no, they know regular graphene, but it's small, 30% level. That's the number I put down, okay?
Thank you.
Certainly, theoretically, that's correct. Experimental information is very little. All right, so the reason we did a very long paper on superconductivity is that we had this question, this is Fengcheng and I, that what if the superconductivity is not S-wave? Normally, phonons only give S-wave, but here you have all this topology chirality. Is it possible that regular electron-phonon interaction here can give you other orbital superconductivity? Answer, of course, is yes. Otherwise, I would be talking about it. So, you know, so if you take this simple formula, you find KBTC is of the order of 1K, but that's not what we are doing here. So what we did the full Eliashberg theory in a simplified way. let's say BCS theory, correct BCS theory, taking into account sublattice chirality. Okay, so you can do that. It's a lot of group theory basically. Okay, and we then found but it's because Feng-Cheng has already done something like this around McDonald before for optical phonons, but I don't think optical phonons play any role here at all. I think it's all acoustic phonon. You find regular phonons can give you S wave, F wave, D wave, P wave, all pairing is allowed because of values and chirality. So again, I'm not going to go through the details. We worked it out totally in our paper. It's completely analytical. And then we can do the full calculation, which we did. And we showed that the original simple estimate actually applies here. Okay, except that you can get, and so let me give you just the phase diagram. Okay, this is just some details on the theory. Let me just keep that. And we linearize the gap. We did the standard thing that people do. And this is our phase diagram. Okay, so you can have the S wave, S and F wave are very enhanced. P and D wave are not as enhanced, but it certainly depends now on the filling. So this could be some weak explanation for why the superconductivity is not seen everywhere. And there could be very interesting superconductivity going on, but this issue is experimentally open. Okay, so they do not know really the pairing, what the pairing is. And our prediction is that all pairing should exist because of the sublattice chirality and how they pair. And this is an open question. And of course, our theories, again, within Bistriger McDonald type band structure calculation, and people of goodwill could say, well, this is a very simple thing, but unless somebody does anything better, this is all what you have. So this will end my electron-phonon part. Are there questions?
Okay, so may I ask a question?
Yeah.
Your phase diagram here shows Fs and F apparently on top of each other.
Yeah.
That's because they're from symmetry point of view, they're not distinguished.
Yeah.
They're really the same statement. They're the same representation of the group.
Yeah, exactly. At all level of theory, they're the same.
Okay.
Mm-hmm. So, and the same for P and D for the same reason. Okay. All right. So now, Jade is in the audience. I'm very glad that I have at least one of his Herculean work. And I think our computer had to be used for this, right, Jed? Rutgers computer wasn't enough for this, right?
Yeah, that's correct.
So this first I'm going to talk about Jed's work, well, Justin's work really. But Jed is the leader here, don't forget. So this is a Herculean piece of work. When Jed was working on all this 3D wire system and using the trick of quasi-crystal, which I'm proud to say he learned at Maryland, right? What happens when you have different periods. My question was that, twisted disorder, can somebody do something about it? And this turned out to be very, very big challenge numerically. So when you twist, main disorder in this graphene probably are not impurities. Andy, going back to what you were asking, it's probably from this twist disorder. And this twist disorder is very subtle. Jade is right there. Justin did a fabulous job. You should ask them. So I'm just going to show some results. These are not calculations I can do even in my dream. So in these calculations, even with very powerful computers, transport could not be calculated. I would love to do transport calculations using this, let me call this band structure calculation, just density of states, okay? That has not been done, but it needs to be done. At least we need to have an estimate of what level of resistivity these disorder contribute to answer Andy's question correctly. That what is the residual resistivity coming from? So what happens when you have this disorder? Well, the density of states is very strongly affected. These are your famous Van Hoff singularity in twisted bilayer graphene. This is at some fixed angle. And what you find is that as you're increasing this twist disorder, they are strongly suppressed, and experimentally, they almost never see these sharp peaks. They're strongly suppressed, okay? So, and this suppression, Jade can give you quantitative results. So this is the same thing plotted in, so you only calculate the density of states here. And so your gap then, typically the gap, regular gap at the band edge, not any of this correlation gap. If you just take the naive theory, it's very large, of the order of 40 MeV. And my guess was, from the beginning, Jade will verify, is that twist disorder will reduce that very strongly. Because experimentally, they always found a smaller gap. So here, how the disorder reduces. And in fact, the disorder immediately will give you a metal-insulator transition, just disorder reduced. Nothing fancy. This is not even Anderson localization. It just goes to zero, not for very large twist disorder. So there is a huge amount of, wealth in these calculations, very serious calculations of Jed and Justin. I have nothing to do with this anymore. I instigated some of the initial things and encouraged them a lot. We spent a lot of time at Aspen talking about this. That's some wearing an Aspen jacket. And this is something, what I would love to see is a collaboration between Rodgers and Flatiron to do serious adult transport calculations using this as input. Very hard, but based on what I heard from Andy and Atwan, it seems like you have the resources. All right, so here is a much simpler calculation, the kind of calculation that I think Yuhan Huang and I have published 100 papers over a 30-year period on all systems and parameters are known. These are through the Boltzmann calculation, serious Boltzmann calculation, assuming you have impurities, either charge impurities or point range impurities. So these calculations are both. This alpha and beta are the parameters that tell you, I forget which one is what. Alpha is either short range or alpha is long range, and beta is the other one. So you have both long range and short range because you have done a lot of work on graphene in collaboration with Philip Kim and Horst Stormer. We have a pretty good idea about short range and long range, and those are the numbers we put. So here you can see, oh no, I'm wrong. This is all short range, this is all long range, and this is all short range. And alpha and beta are really the strength of the, strength of the Van Hoff singularities. So basically, Andy, answering your question, this is what happened. This is a residual resistivity as a function of density. And the thing we're trying to understand here is something this student, Yankowitz, who was, I think, Corey's student at Columbia. Yankowitz, I think, was a student at Columbia, I'm not so sure. I think he was, because first thing I ask anybody says, if they're students in Columbia, have they taken a student of course from Andy Millis or Igor Alena? So I think he told me that he did. So Yankowitz asked me a question. He said, do you understand this tape-like structure? At very low, this has nothing to do with what I was talking about. He noticed that there are these steps, and this is at many. And so this is what instigated this calculation that Yuhan Huang and I did. So normally our calculation doesn't include Van Hoff singularity. Here we included Van Hoff singularity and immediately found steps. And these steps are very easy to understand. Something is kind of diverging. So this step-like structure is when things are not diverging, okay? And again, all I can tell you, answering Andy's questions, there is no experiment kind of accurately trying to, you have all these parameters. I'm sure you're going to be very happy to work with experimentalists to answer the question Andy had. If you extrapolate what you get and so on and so forth, all I did is a little discussion with Yankowitz. They look consistent within a factor of 10, okay, in the numbers, Andy. That's the answer to your question, okay? But these steps are explained, and these steps may very well come from Van Hoff plus impurity scattering. So this is my end of my transport discussion. So if there is no question, I'm going to totally change gear now, talk about pure correlation effect, no impurity, and no phonon, just electron-electron interaction. So if there isn't any question on that, you could ask now, but of course you could ask later. Okay, I don't see any questions, so let's go to transition metal dichalcogenide. So in graphene, all our correlation work is very high-powered RG work, because by the time I entered the field, Alan McDonald has done all the Hartree-Fock and simple calculation. He didn't leave anything for me, and Mike Zalato, okay? So there was nothing for me to do with simple theory. So we did a third, I'm very proud. Robert Throckmorton spent one whole year, and we did a 32 parameter RG, okay? All the other RGs are one parameter. With symmetry, brought it down to 12. but we did 12 parameter RG. What is the answer? Can anybody guess what the answer is? Answer is every phase anybody knows is allowed. Because there is so many symmetries and so much is going on since RG cannot tell you anything more. Everything is allowed. So, and they'll be all very fragile because they're all competing with each other. So you wrote a long paper saying that. But in transition metal, we were among the first, so we did a lot. So what did we do? So now we are doing quantitative calculation because we have a pretty good idea about what the Hamiltonian is. So we started talking about things I don't like using in the title, quantum phase diagram and so on. I'm going to use the word quantum phase a lot, but everything I'm talking about here is not the kind of calculation you guys do. These are all mean field, restricted or unrestricted Hartree form. They're all quantum calculations. Take into account spin, take into account orbital symmetries, but they are not, they don't go beyond mean field. Okay, I just want to make that very clear so that people do not give me trouble. It's just, that's what we do. Okay, that's what needs to be done first anyway. So we can calculate various gaps, but filling factors. So, you know, this is just the conclusion of the paper work, but I'm going to show you. Looks like many known and many unknown quantum phases may be lurking. An excellent system for doing physics, and much is still undone. Not as many people are working on this, and some beautiful data coming out just from 100th Street, just a few blocks up from Flatiron at Columbia. Corey Dean is doing some of the best work in this. Corey Dean and Ave Prespati are doing some of the best work. So let me first explain the difference between graphene and TMD. They're very similar, but there are some significant differences. They're very similar if we do the kind of theory I used to do before, effective mass. But here we are taking into account the correct. So is D6H gets less symmetry here. Things are easier. Strong spin orbit coupling, vanishing spin orbit coupling. So they're just two. The ground set has just two degeneracy. A gap opens up. Really, the system is much, much simpler for many body calculations. Much, much simpler. So the standard Hubbard model, Mott-Wigner type model applies. On the other hand, here, there is a lot of like Charn effect. So you have quantum anomalous Hall, which I didn't talk about. Our most well-known work in twisted bilayer graphene is actually establishing that it's a quantum anomalous Hall because of the Charn number being finite. I didn't talk about that because that would take one whole talk by itself. Here, there is no magic angle, okay? So we have two valleys, one spin, one band. Much simpler system. Look at this. This is two valleys, two spins, two bands, two valleys, one spin, one band. Beautiful, my kind of system, okay? So the first thing to do is to do the band structure. So the band structure, this is what Fencheng and Heining did. They have Fencheng has a lot of experience. You have to take into account spin valley locking. It can be done. So this is the equivalent of Bistritz or McDonald for twisted, and you have to do it homobilayer, heterobilayer. That just means whether the two layers, I didn't explain that, the two layers, whether they're the same, are you using tungsten diselenide in both, or are you using different? I'm not going to make this distinction. Most of what I'll show you is homobilayer. Alan is doing mostly heterobilayer. We are doing mostly homobilayer. But I do not think at this level the difference is huge. Difference is quantitative. So you get various bands, and some of those bands indeed have non-trivial topology, meaning they have Charn numbers. But it turns out the experiments are mostly in holes, and they're mostly in the trivial band. No experiment, as far as we can tell, have so far been done in the regime where the Charn number is non-trivial. So all the theoretical results I'm going to show you are in the trivial band. So there will be no topology, okay? So we have a band structure. Now, to do many-body theory, since we do not do many-body theory we cannot do, I should say, arbitrary band structure, you have to parameterize it. So the natural parameterization here is in terms of three parameters, which we call V, psi, and W. That's the best natural parameterization. So that's what we did. And we extracted these parameters by comparing experimental STM from Pasupati and also, I think, a result from Cornell. Their data, we literally compared and extracted our parameters, okay? So this is semi-realistic, not as realistic what your group does, but this is the best we can do. Well, then we have these the hopping amplitudes, and you need at least next nearest neighbor here to keep the correct physics. And this is our Hamiltonian. In Hamiltonian, we know everything. This is hopping. Since we calculate the 1-year orbitals, we have this actual band structure number. And U is ordinary Coulomb interaction, is square over kappa R. And again, since we know the 1-year orbitals, we calculate the matrix elements of U correctly to, I think, to 2000 next nearest neighbors. These are fairly large calculations. So we are calling it Hubbard model, but it really is, this is not the naive, pristine Hubbard model. This is not one U and one T. This is many T's and up to 2000 U. So tight binding model plus interaction, we can calculate full phase diagram. Question mark here means, of course, we are calculating it within some approximation. But here we have the advantage, nobody has done it before. So we can, so the scale, if you want to know, the Moire unit cell size is this, and for tuning, and these are the densities, and these are the typical numbers. So U over T is roughly maybe 10 to 50. Okay. So you really, for a large range of theta here, this is the advantage, you get strong correlation. You do not need to fine-tune theta to very close to 1 degree like you need to do in twisted bilayer graphene. Twisted bilayer graphene is very fragile because you have strong coupling, as I showed you, only when the velocity is very small. And we can do now the calculation. So this is our, U of R matrix element, and we take into account the fact that you have an image charge. So again, what I mean by semi-realistic is that we're doing a pretty honest calculation from the band structure. You're all very familiar with what I'm talking about here, okay? All right. So no, I was wrong, not 2000. This is what Heining told me. 15,000 next neighbor terms, and we get, I guess, convergence there. I always insist on convergence with the students since I don't do the calculations, and it always takes another month. So what do we start? Interesting. This is a very important point. We start from the classical limit. In classical limit, we can solve this problem analytically. Okay. And we know what the various Wigner crystals are from the symmetry. We know everything about it, okay, about the problem. And this is, I think, the new idea we introduced. So you get stripe depending on filling, because each filling corresponds to a different geometry. So you can get all kinds of Wigner crystals, okay, with their own energies. So that gives a starting point to do our self-consistent calculation. Then we add spin, and we do the occupancy and do full quantum Hartree-Fock. So we start from classical ansatz and do it. So here is, for example, an actual calculation. And this background dielectric constant here is roughly 10 for these materials. This is something we have to take from experiment. You have boron nitride, and then you have this tungsten diselenide. And this is our calculated gap, correlated insulating gap at different filling factors. And at 1, of course, is the largest. 1 is half filling. Here, that's our notation. And this is the experimental measurement from this Mack and Shan's group at Cornell. And Feng Cheng and Hai Ning were overjoyed seeing this, because this looks very good. And I asked them not to pay too much attention to this thing, because these things may change and so on. But it's at least in the same ballpark, okay? The problem is these are really optical gaps, so one should be careful. So what is the phase diagram? So this is the phase diagram at half filling. Our notation changed. I mean, even I was confused by notation. In the original paper, nu is equal to half is his half filling. And our current paper, nu is equal to 1 is half filling. So this is the half fill, but no, is it a half fill or is it a Heining? Is it half fill or is it 1/4 filled?
Oh, this is one. Okay. This is
half field, right?
Yeah.
This is 1 electron.
This is half electron per side.
So this is 1/4 filling.
Right. If you consider the
so this is 1/4 filling. Right? So it's half. Oh, you changed the notation. Okay, good. So this is half electron per side, 1 electron for 2 sides. So this is quarter filling in the Hubbard language. Okay. So you see what we are finding, and I'm going to show you other also. So here you have an antiferromagnet, standard antiferromagnet, and that's everywhere. But this is only for epsilon very small, so very strong Coulomb interaction. And it quickly gives in to the ferromagnetic insulator. Okay, so the experimental situation is actually ferromagnetic insulator. That's somewhere like 10. Okay, very stable as you can see. Then as you decrease interaction, so we have 2 tuning parameters, theta and the dielectric constant. This is theoretical calculation. We can make the dielectric constant anything. Now we are doing calculation with 3 tuning parameters, epsilon, theta, and d, the thickness of the boron nitride, and those results are still happening. So then you get a Kagome. Then you get then you get a Kagome C2Z breaking. Then you get a Kagome time reversal breaking. Then you get a ferromagnet which is metallic, and then you get a tetrahedron. We could not find any name for it in the literature. Nobody has talked about this phase before. And then you get a normal state. So the point I want to make that this may not exhaust it. If you do a better calculation, I'm sure you're going to find other states. There are lots and lots of correlated phases already within Hartree-Fock calculation. Okay, this is what you expect. It's a very rich system, and there is very strong interaction. Let's go to another feeling. So this is nu is equal to 1/3, 1 electron for 3 sides. Nu is equal to 2/3. And you can see phase diagram does depend on the feeling very strongly, as it should. And here, for example, experiment should only see the standard antiferromagnetic insulator. Here, on the other hand, experiment should see only the ferromagnetic insulator. It's like very specific prediction. And I'm hoping the Avai-Pasupati will do spin polarized. By the way, in no system, twisted bilayer graphene or transition metal dichalcorogenide, is there any information about the spin structure of the ground state, except for this a little, hysteresis, a little quantum anomalous Hall at that level. I mean, that's not quite ground state information. We need spin polarized STM. Okay, but this is what the theory predicts. Then, once you have the program, you can do other things. I'm not going to go through all these things. You get the idea. Many, many different phases, some phases people talked about, many of the phases nobody has ever talked about shows up. Okay. Are all of them visible? No, because you cannot change epsilon continuously. But it's very interesting. And we'll see how many of these phases we find when we vary d, small d. So rich and complex competing phase diagram. Competing meaning the energy difference between these ground states is very small. We are publishing a paper on that now. Okay. Abundance of various symmetry broken phases. So very recent work now. I'm coming towards the end, but a very important point is still there, which you have to stay even if I go over time. So very recent work motivated by questions that Corey Dean asked me over Zoom recently, and then Avai-Pasupati and their whole group got involved. We had several very intense Zoom meetings. So what they were finding, and this is paper they're writing, which I'm sure will go to a glossy magazine, what they were doing experiments slightly away from specific feelings. They're looking at a little bit away. They're doping a little bit, which is what they do. And they're finding, doesn't matter what feeling they start from, 1/2, mainly the nu is equal to 1. So half field, the Mott state situation. They find the moment they dope away, it becomes a metal, like high TC material. So they're very excited about it. So they asked us if we can do these calculations. So these are all this calculation. So now what we are doing, we are sitting at some fixed angle, theta is equal to 4 degrees. So nu is equal to 1 is half field, 1 electron per Moire site, right? And so I told you that's all antiferromagnetic insulator. Okay, so it's our theoretical, all antiferromagnetic insulator. And then you have a normal metal. I'll explain what these two are in a second, what these two figure. But both of them correspond to nu is equal to 1. It's all antiferromagnetic insulator. And then what we are saying, well, Let's go slightly away from nu is equal to 1. Let's go to 19/20, 14/15, and do a calculation. What we find, the moment you go away a little bit, we find a ferromagnetic metal. Now, what the two cards? This is, I asked Heining, I said, well, it's not enough to just do ground state. We have to look at competing ground states to see what the energy difference. So here you can see the ground state energy difference between ferromagnetic and antiferromagnetic insulator is small. And so we are giving you both energies. And so one can calculate the gap also, the separation that's on this side, okay? So you can see here the ground state is an antiferromagnetic metal, the blue line, but a ferromagnetic over here, okay, for epsilon is equal to 10. This is epsilon is equal to 10. The experiment is on somewhere around this dashed line, just to the left of the dashed line. So just to the left of the dashed line, you have a metal. That metal could be antiferromagnetic metal or ferromagnetic metal, spin density wave or just a ferromagnet. But it's very close to the insulator. These things are vanishing and then the insulator takes over. So what I'm trying to say is it will be very fragile, but you'll have a metallic phase close by, which is apparently what they're finding. So this is very exciting. So he calculated gap. These are the gaps for various states. This is the paper we have submitted, being refereed. Referees liked it. So I think it's going to come out in his letter. And it's a very exciting finding. The metallic phase nearby. We have done this at some other fractional filling also. For some fractions, this doesn't happen in as robust manner. For some fractions, they do. We are trying to understand it. The paper we have is really only for the half field nu is equal to 1. Okay. So I'm not going to talk much more about it. Let me just explain to you what this is. These are range dependence. I noticed very early on, so this is the result when we have the full Coulomb interaction, full long-range Coulomb interaction. We calculate the phase diagram, and you find antiferromagnetic insulator. This is the classic Mott insulator. This is in the Mott-Hubbard literature, this is called half field. 1 electron per unit cell. And then it goes to a metallic phase for very weak coupling. I noticed that whenever you do the long-range interaction, the antiferromagnetic phase is enhanced, which is like counterintuitive, right? Because antiferromagnetic phase is suppressed. Metal phase is enhanced. This is the full interaction. This is the standard Hubbard model calculation. Standard Hubbard model, just on-site interaction, but say for the nearest neighbor, because you have to reproduce the band structure. And Hubbard model is on-site interaction. And I was puzzled. I said, why would the antiferromagnetic phase be suppressed when you have more interaction naively? I mean, for experiment, it doesn't matter. This is all happening at very weak interaction, but it puzzled me. So I made poor Heining spend a month on trying to figure this out. I was sure there is a mistake. There is no mistake. This is a real thing. And you can very easily do accounting and show this is what happens. Because what happens with Pauli principle, when you hop, the energetics changes. And it's indeed true that the long-range system, the metallic phase is enhanced. You can just, listening to me, you can do it in one dimension. Just do the counting, and you'll find that, and for 2D also, you can do the counting, just simple counting, just classical counting. And this is happening in quantum mechanics also. So one pure prediction is, and maybe others know it also, but I didn't see it anywhere. Maybe this is very well known because I'm not a strong correlation person. This is real. So there is a range dependence. So now we are doing this range dependence in complete gory details. And these are some of the results, which I'm not going to go through, that when you do calculation as a function of number of shells, including the interaction. One shell, that's just on-site. 2 shells, which is called extended Hubbard model. On-site Hubbard model, next nearest Hubbard model. 3 shells, 4 shells, go all the way to 20,000 shells. How does the phase diagram change? It is the kind of things that people who are doing computational physics trying to understand something will do, but I'm very interested in it. And the phase diagram does change in some fractional filling quite strongly. In some other filling, it doesn't change. As you can see here, some other phases showing up. I don't have the time to discuss this in details, but it's a very interesting question which we're working on now. Okay. Now I'm going to talk about the last topic, one of the most interesting things that we discovered in this subject. It just came out as a physics letter in we and myself. I do a lot of work on incommensurate localization. I have been doing it for a very long time. I have been doing it since, I think, Atwan and Andy were still in graduate school. Well, not quite. Andy, you graduated in 1984, right? Your PhD? Yeah, so that's when I started, Richard Prange. Question is, Aubrey-Andre model, that localization doesn't just happen because of disorder, it can happen because of incommensuration also. My puzzle was, all these Moire systems are incommensurate systems. For any arbitrary angle, you have an irrational. There is no Moire unit cell. Bistrither and McDonald lied. They did a coarse-grained continuum, so they got a band. And really, there should be no band. If I were God and I can look at things with infinite precision, that thing is like a quantum dot. Twisted bilayer graphene is just whatever it is. Nothing is repeated. Repetition comes only because we cannot approximate an irrational. We always approximate irrational with the rational. So let me give an example. Suppose I create in one dimension, we can work it out completely. And I have a very, very smart student in Wu, who when he started working with me, he didn't know much solid state physics. He was doing laser optics before. But he got a perfect score in the qualifying, so I had to take him. So I told him, this is the problem. If you know quantum mechanics, you can work. So I said, work on incommensurate localization. You have two lattices, one lattice, and you just use this, and A1 and A2 are irrational with respect to each other, so there is no band. But for any rational approximation, so let's say A2 is 1.4 A1, okay? So now you approximate this by 14/10, so you get 7/5. So 7 unit cells of this and 5 unit cells of this together give you a Moire unit cell. But in reality, if you use this in the square root of 2, which is what we used, there is no repetition at all. In reality, there is no Moire unit cell. If I were God, if I were like Cantor, and I was really trying to represent square root of 2 to infinite precision, this thing will never repeat itself. So there is no periodicity. So let's try to understand what this lack of periodicity does by systematically approximating irrational by higher and higher level rationals. Okay, this has not been done in 2D. I originally wanted to do in 2D, but you guys can do it. I cannot do it. And this needs to be done. The referee thought that this may be playing a very important role in 2D system. So here is our Moire system, and now we always keep this to be square root of 2, but we keep on approximating by larger and larger m. If we take 1.41, well, in this 141 by 100, we can do anything we want, and then we can do exact calculation. We do not need to do Hartree-Fock. We do not need to use any approximation. You don't need to do DMFT, quantum Monte Carlo, anything, or DMRG. Heck, we can diagonalize that to 10, 12 electrons ourselves. We have a large enough computer. And look what is happening. We can change interaction. We are using Coulomb interaction here, by the way. From 2.5, just m is equal to 1. Approximate this by 1. Approximate this by 1.4. Then go to m is equal to 8. Already changes from 2 to 600, 300, nothing else. And look what happens. This is the actual charge density. From a completely metallic state, but the electron is everywhere, to, if you look at it, pretty strongly not localized state. Now the question is, so we calculated gap and all the things, okay? Here is the 1-year function, shows you that it's very localized, very little overlap, and we can continue. We can do for whatever capital M you want. So I'm going to finish. I've gone way over time. So here are some results. We did a beautiful piece of work here. Here are results for different values of n. We calculated the gap all in half filling. And as you can see, gap systematically depends on the value of capital M. So if we take M to be 1, black, nothing, no gap at all, as there should not be. This is the original period. Well, we go to M is equal to 3, green. Well, you cannot really see the gap. If you magnify it a lot, there is a little gap here. M is equal to 7. Well, now you see a gap. m is equal to 8, you see a strong gap. We can then make the system size larger. Why does the system size matter? Because if you make the system size larger than the Moire unit cell, you don't have the periodic physics anymore. So here we are keeping the value of m fixed, changing the system size. So Moire unit cell size here is fixed, and see what happens. As we change the system size, well, the gap energetics, correlation energetics changes drastically. This is the competition between incommensuration and interaction, which you are not going to see in the continuum limit at all. It's coming entirely from the system being discrete. And it will have enormous effect on anything you measure. And I personally believe this is the clue. This coupled with the twist disorder that Jay Pixley talked about is the clue to why the correlated insulating phases are so fragile in twisted bilayer graphene. You know, superconducting phase is much more stable than the correlated phase. Correlated phase, somebody sees it, somebody doesn't see it. They change something, it goes away. It's, you know, its activation energy is small. It's extremely fragile. And I really think that this physics is playing a very important role. And the only way to settle that is not our model calculation for 1D, is doing this calculation for 2D TBLG, which real adults at Simons can do. I cannot, but I don't want my name on the paper, but I'd very much like to be involved. I'm very interested in this question, having worked on interaction and incommensuration all my life. And you know what? That's where I'm going to stop. How much extra time did I take? Oh, this is bad. I took half an hour.
Look, it's great. Anyway, look at Sankar. Thank you very much. This was a wonderful talk. Indeed, very shortly, I have to bow out because I have a meeting starting at 1.
Yeah.
But thank you very much on my side for this inspiring talk.
Yeah, but feel free to ask me questions, Andy, because if you don't ask me questions, I'll think that I wasted my time. Okay, that means Andy accepted everything. Then it's not the Andy I knew. I want to hear, I'm skeptical, okay?
Okay. All right. So look, we'll get back to this later. I wouldn't say skeptical exactly, but the two questions that come to mind about your previous results are the relation of your ferromagnetism near the Metal-insulator boundary to the big literature on the Nagaoka phase, Nagaoka phase in the ferromagnet. I mean, there's a whole big literature, and the general opinion is one should be a bit scared about the Hartree-Fock calculation, which rather overestimates ferromagnetism.
I completely accept it. We clearly say it in our paper, and I told Ahai that, you know, because this is, you know, the thing is that we're not doing a magnon calculation for transport, because the ground state is a ferromagnet, but there are magnons, and all of this could be just, you know, hot air, because the Hartree-Fock theory doesn't apply at all. I completely accept it.
Yeah. And coming back to your expansion of the metal phase, are you changing the range of the hopping or simply the range of the Coulomb interaction?
Yes, Coulomb interaction. Hopping, the 3 parameter and 3 nearest neighbor reproduces our band structure very well.
Okay, so, but in these calculations, the hopping is fixed, and what is varied is the range of the interaction.
Correct.
Right.
And the hopping is 3 nearest neighbor, up to 3 nearest neighbor.
Yeah, but doesn't in effect, isn't this understandable just by going to the strong coupling limit and deriving what is the effective Heisenberg model as a function of U and V?
Absolutely. That's what is going on. Yeah.
Okay.
Yeah. That's exactly what is going on. You put your finger on it. It's value of J is changing in the effective Heisenberg model. Yeah.
Right.
That's what I meant by simple counting. Yeah.
Right. Great. Okay. Look, thank you very much. As I say, I'm sorry, but I have to run away, but other people should feel free to stay.
Yeah, I'm here. I'm not in any hurry. I'm home all the time, you know, because there's nothing going on outside. So Andy, bye. Good seeing you. Okay?
Good to see you. Thank you very much. And we'll talk more soon.
Thank you, Sankar.
Okay. And if there are questions, I'll answer, but I'm sure everybody's exhausted. I'm not exhausted, but if there are questions, I'm happy to answer, okay? Because I'm not doing any more Moire. By the way, my best decision is not to talk about Moire, because all of you asked me about what did Leo Cohn know, and when did he know it, and when did Microsoft know, and when did they know it, okay? And I would have said, I knew it all along, it's not Moire. In all my talks, I was saying it, okay? But nobody was listening to me. Anyway, are there questions on what you presented? Sorry.
I have a
Please.
I have a
Hi,
mundane.
I haven't seen you in a long time. Hi.
Yeah, nice to see you. How are you doing? So my question is the in the twisted TMDs, you mentioned these regime where you get churn numbers in the bands. How do you get into that regime? Like, I mean, I looked at your paper, you add a diagonal potential, but like, how can you access that experimentally?
Doping, just changing doping. So you have to fill that band. You have to push the Fermi level there.
I see.
Okay. So we, this is something, of course, our band structure may be wrong, but it's just going into that band. It's something as simple as that.
I see. Because I guess that I thought that you needed to add, so in other words, if you're making a twisted Hamiltonian, you can have interlayer coupling. And I thought that the churn numbers were coming from having diagonal couplings. And I didn't know if those diagonal couplings, if the magnitude of them, I don't know how to estimate the magnitude of those couplings.
Yeah, so there is, this is something really Heining should answer. You do a real band structure calculation. And I skipped a part. They actually have an electric field along the particle direction also, which changes things also. So that's, it's in our first paper. This is all explained in our first paper, which we didn't talk much about. You should look at it, and if you have questions, feel free to send them to me, and you can work with Heining. I want to stay away from anything with the word churn and topology for a while. Okay, so but Heining, I'm sure, will be very interested. He's very good. This is a good question. That are we simplifying things? But I gave you an honest answer that our current belief is by doping, they should be able to go there. And where they are now, our theory is also saying they're in the trivial band.
Yeah. And then,
when I say doping, I'm including the electric field as part of doping.
Yeah, sure.
But they're really different things, okay? Because one is tilting the bands also.
Yeah. Okay, and then the other question I have, which is also quite easy, I think, is what's the fundamental reason why the dependence on twist angle is so much less in the TMDs? Is it just that it's quadratic band?
Quadratic, band gap. Okay, so those two, it's a quantitative details,
Yeah, okay.
The existence of band gap and quadratic, this is what makes huge difference. Already in, double bilayer graphene, which is quadratic, these effects are much less. I mean, they're there, but no one near as strong. There's only one paper, I think, on double bilayer. Twisted double bilayer.
Yeah. Okay, I see.
I have a quick question on these.
Hey, you can ask me a long question. I have nothing better to do. Okay, I mean.
on these long range ordered states, and these are forming on the Moire pattern. Is that correct?
Say it again. I didn't understand the question.
These long range ordered states you're showing on this slide, they're forming on the Moire pattern.
All of them in the Moire pattern. All of them on a finite angle.
Yeah. So your critical temperature is incredibly low because it's huge lattice spacing, or I mean.
Critical temperature is low. That's what we have. That's what the gap energies are. They're not that low. I showed you that gap energy. So it's actually in Hartree-Fock theory, they're huge. 30 millielectron volt. I would not call that low. Yes. So this is for here. I'm sorry if you missed that. You missed the whole talk. Of course, everything is model. You'll see nothing in non-twisted system. Okay. So this is this is real. This is the real experiment. Okay, this is the Cornell experiment. This experiment is done at 150 Kelvin. And you can see experimentally what they're claiming. Our numbers are even larger by factor of 2. Okay, experiment is claiming they're finding critical temperature. So you see, the thing is, Jed, I know exactly where you're coming from. You are QMC, you are Kondo-Hubbard, heavy fermion. Energy scales are completely different here. This is why you work in semiconductors. And this is like, I wasted my life in gallium arsenide trying to see strong correlation. This is the system where you should go. Okay, so the numbers are huge. Everything that we thought of before as 10 millikelvin is 100 Kelvin here.
Interesting. Okay. Yeah, I just would have naively thought, like within a mean field sense, you'd have a very small, because the lattice spacing is so large on these Moire scales.
These are this is what small is here. Okay, that's what I'm trying to say. I'm trying to say is that your intuition is correct, but your numbers are wrong. It's coming down from electron volt. Okay.
Yeah. Thank you. Yeah.
So these calculations I believe in because I didn't do them. Heining and Fengcheng did it. These numbers make perfect sense to me. I checked that. these are the numbers I expect, a scale. Remember that all numbers here, this is like 300 Kelvin, and they're saying, no, it's like 40 Kelvin. So maybe a factor of 10 wrong. But these numbers are huge. And hardly fuck you expect the gap to be, smaller.
I see.
Did I answer your question? Because it's a very
that answers that exactly answers my question.
Because remember, when there is a unit, small has no meaning, right?
Yeah.
Okay. I mean, what is small? You need to look at dimensionless unit. Dimensionless unit, these are very small.
Right.
Because U is 1 electron volt. Okay.
Great. Thank you. Yeah, nice talking to see you.
How are the children doing? Jed?
Increasing.
Oh my goodness. Hello, this one I didn't see. Right?
You haven't met her yet. This is Matilda.
The one who was running along the street almost naked. How is she doing?
She's still almost naked, but she's 4 now. So
okay, yes. I'm sorry, Go
I
on.
know, fine.
Yeah, there's a question.
Wear clothing. That hasn't changed. So good to see
somebody
you.
else had a question. Please ask.
Hi, Professor and Sarma. I have a very naive question regarding to the last part of this work. So you mentioned
the incommensurate part. Is it the incommensurate part?
the Moire versus the mod.
Yeah, let me go there. Yes.
The last slides. So you mentioned
the last figure. This one.
Yeah. No. You mentioned that there's an interest in generalizing in 2D systems. So my simple question is, what is the numerical difficulty in 2D? Is that because of the large unit cells and interactions?
These are exact diagonalization.
Yeah.
So how many electrons can you do even over there for 2D? Okay, that's as simple as that.
Okay, I see.
Yeah. So the thing is, that's the only difficulty. I mean, formally, I wrote down the theory when Inwi and I discussed for 2D. And in fact, I asked Fengchen before I involved Inwi. And Fengchen thought it was a very good idea, but was looking for a job. And, COVID has already come, and it's very hard to discuss anything over Zoom, explain these things. Inwi and I go to work every day. Okay. So we go to work every day, so we could talk face to face. So that's how it could be done. This was, so a main problem would be that I do not have a computer large enough, but the same calculation can be done in 2D, probably with you do not need to use 100 electrons. This will show up. This is, 2D, you need effectively more electrons, right? For the same result. So this result is already showing up. Look at our PRL. This result is already showing up in this glory with 3 electrons in 1D. So I suspect we go up to 12 electrons to show our muscles, but only 3 electrons. So I suspect with 10 electrons in 2D, you're going to see this physics. Okay.
Okay, I will take a look at this.
Yeah, and then communicate with who.
Thank you.
Who we are not going to do this anymore because we now wants to do topology. But this is a very important question. What role is this physics playing in TBLG experiments? If this is playing a role, those insulating phases will never be very robust. Okay, so talking about switches and all those things with this would become like talking about quantum computers.
Hi, Sankar. This is a great talk. And could I ask a question on the phase diagram of the twisted bilayer WSE2? It's like
okay, let me go to the phase diagram. It's easier for me to focus.
This one.
This one?
No, like the previous page. It's like I guess it's later. It's like the ferromagnetism and antiferromagnetism, like the.
Okay, all right. So you mean for the when we are looking at the metallic phase also, right?
I guess it's just like around half filling.
Yeah. Okay, I know what you're asking. Let me go there. I know exactly this one.
Thank
this is half filling. This is half filling.
Yeah, it's just a very naive question. Like for the antiferromagnetism, is this referred to the 120 degree or
exactly? Others have asked me this question. We tried to use the same language every. Yeah, that's what it is. It's 180 degree, exactly. And I had a figure which I didn't show, showing all the phases. It's in our first paper on nomenclature.
Okay. And also, like, could you explain like why is there a gap like away from half filling? It's
well, I mean, what you are asking, you're very smart. What you're asking, why should there be a gap? Let's say 14 over 15. It should be like half filling, right? If you do Hartree-Fock. So obviously you're not doing just Hartree-Fock here. I did not want to go into those details. We are doing a perturbation theory to get the gap. Because if you do Hartree-Fock, you clearly have understood this very well. If you do Hartree-Fock, for all filling, there'll be gaps. And what Jade was saying is going to happen. The size of the gap will go down as this denominator increases, okay? So we have to do an alternate theory. So this is not turning the same crank. We had to do a perturbation theory to get this gap, okay?
Okay.
So what Hartree-Fock gives here, answering your question honestly, is still an insulating phase with much, much lower insulating gap energy, but still an insulator, okay? So then what we said is that, is it possible that this insulator will go unstable? And then we did a perturbation calculation in interaction to get these gaps, okay?
Thank you.
And all of you can communicate with me or my co-authors. Without me, I will not be, at all embarrassed about that. Even if you send to one of us, you'll go to the other person. If you have serious questions or something that's not clear, or your paper don't understand something, the whole point is the subject is still very, very interesting, very, very exciting. And we don't want this subject for the young people. I think only young people are left. We don't want this subject to become like Q-prits, where the problem is that, not that the problem is not solved. The problem is solved so many times by so many different people, all of whom are sure that theories are correct. Unfortunately, those theories are mutually exclusive, so you have no consensus. We want to avoid that. That did not happen in fractional quantum Hall effect, right? We all agree on the main picture. So that did not happen in superconductivity of regular metals. We all agree with them. And that's what I want here. This is a beautiful system with all kinds of phases, and we really want to know what's going on. Is it really true phonons are causing strange metal behavior? Is it really true that this Hubbard-type calculation at a mean field level is telling us something about the phase diagram? These are the kind of questions we should address. And with big computer and technical skills, one can make progress.